Greetings and welcome, friends. We're in a new chapter. We're talking about graphs of trigonometric functions, right? So we're going to be actually graphing some of our trig ratios later on in this chapter. It's going to be quite interesting. They have a lot of interesting behaviors and applications within the real world, actually. But today, before we even get there, we've been familiar with using degree measure to talk about the size of an angle, right? We've talked about standard position. We've talked about all sorts of different angles, reference angles and coterminal angles and blah, 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 right? But today we're actually going to talk about a different way of measuring an angle, okay? So let's think about the unit circle real quick. Oh, that's not that bad. I'm quite pleased with that, I might say. So if we think about, or actually just maybe even any old circle with radius r, okay? And a radian, all right, is going to be a different way of measuring an angle. Instead of thinking as, our arc, or our little angle measure here between two sides and a vertex and the number of degrees that is, we're actually going to measure our angle based on this arc right here, all right? So I'm going to measure it based off of the arc. And we're going to use a measuring stick, I guess is how I'd say it, that is going to relate to every single circle. All right, so we're going to use the measuring stick of a radius. All right, and my circle's not perfect, so this isn't going to line up perfect. But imagine if I took this radius and I asked, how far would this reach if I was wrapping it around the circle? All right, so something like that. All right, so this would be r units along the curve of the circle. All right. So that measurement around the circle creates an angle, all right? And the size of that angle would be called 1 radian, okay? All right, 1 radian. So I guess the way I would describe radians, all right, a radian is an angle measured by the number of times a radius fits into the arc, I guess. The radius into the angle's arc. You could even say the angle's intercepted arc if we wanted, I suppose. All right, so 1 radian looks something like this. All right, and it's, so I mean I could have half a radian, all right? Right, I could have like 2 radians would look something like this. All right, and that'd be a bigger angle. So you could have all sorts of different measurements. Now my question for you is, how many radians do you think fit all the way around the circle? Now my circle's not perfect here, but yeah, how many radii, right? How many times could the radius, how many radiuses, if I want to say it that way, would it take to wrap around a circle? Well, let's think about that. The distance around a circle, what formula do we use to talk about that? Circumference, right? And circumference is equal to 2 pi r, right? So I'm basically asking the question, all right, what do I get when I take c, the circumference, and divide by a radius, right? So I can actually do that right here. I could take c, and notice with this equation, if I divide both sides by the radius, c divided by r is the number of times the radius fits around a single circumference. And if I simplify this formula, I'll get c over r is equal to 2 pi. All right, because these r's would cancel out. And 2 pi, decimally speaking, is approximately 6.28. Actually, let's go a little further than that. 2 pi is 6.2832 roughly. All right. So 6.2832 radians is the same as one full circle. Same as one revolution around a circle. Okay, so 6.2832 or 2 pi, we're typically going to use the non-decimal measurement for our radians here, but there are 2 pi radians in a full circle, just like there are 360 degrees in a circle. So I guess maybe that's another fact I could write down here. So 2 pi radians is equal to 360 degrees. So there's kind of a fact that you could use a little bit to convert between the two. So if I wanted to find out how much 1 radian is in terms of degrees, well, 2 pi radians is equal to 360. One of the things I could do with this equation, I suppose, is we could actually divide both sides by 2 first of all. But let's just say I divide both sides by 2 pi. Right, because 2 pi divided by 2 pi is going to be 1. So I'll have 1 radian is equal to, and 360 divided by 2 is 180. And pi would still be left on the denominator. So 180 divided by pi degrees, which is approximately 180 divided by pi. Pi is about, right, 3-ish, so it should be around 60-ish. And I get that's about 57.2958 degrees is 1 radian. All right, so not often will we necessarily need to convert between the two, but sometimes people like to convert back to degrees because that's helpful for them. They're more familiar to that format, and we'll be able to convert back as well. So this angle here is about 57 degrees, all right, for 1 radian. The length of the arc in which a radius wraps exactly once, so to speak. So that's what 1 radian is in terms of degrees. So that's a good little fact to know. So what would 1 radian, 1 degree be in terms of radians? All right, if 2 pi radians is equal to 360 degrees, how would I get a relationship where I just have a single degree here? What could I do to both sides of this equation? Yeah, right, because 360 divided by 360 is 1. So in this case, I'll end up getting, I'll flip this around as well. So 1 degree is equal to 2 pi divided by 360. It's the same as pi over 180 radians, right? Which is approximately, let's see, pi divided by 180 is 0.0175 radians. Okay, so 1 degree is a very small number of radians. All right, so those are kind of two facts that can help us convert, so to speak, from one to the other. So it's typically related to this pi over 180. So let's do actually our first examples, or let's do some conversion. So let's convert 330 degrees to radians. So 330 degrees, if I want to convert that to radians, well, it turns out I can multiply, right? If one of these degrees is equal to pi over 180, then 330 degrees must be 330 times this value, okay? Right? I need 330 times this 1 degree to get 330 degrees, so 330 times that. So that's going to be 330 times pi over 180 is going to convert to radians. And we typically, I don't want the decimal approximations as much. Typically we'll want to leave this in terms of pi. And in order to do that, I'm going to just reduce this fraction as much as possible. So between 330 and 180, I think 30 goes into both of those. 30 goes into 330, what's that, 11 times? And into 180, 6 times. So it looks as though this is going to simplify to be 11 pi over 6 radians. All right, so this is an equivalent measurement to 330 degrees. It's just measured in radians. And typically, I'll throw the pi symbol, leave it up in the numerator. Technically, you also could write that as 11/6 pi if you wanted, but usually we'll just leave the pi in the numerator. That's just as easy. Okay, so there's our first convert problem. Let's try converting the other way. Convert 2 pi over 3 radians to degrees. So let's see, let's consider this. So 2 pi over 3 radians, well, if 1 radian is equal to 180 degrees over pi, I want 2 pi over 3 radians, so I could multiply this by 2 pi over 3 and multiply this by 2 pi over 3, and that will end up giving me the degree equivalent. So in this case, I'll take the 2 pi over 3, and I'm going to multiply by 180 over pi this time. Let's see what cancels out. The pi's cancel. 3 and 180, 3 goes into 3 once and into 180 60 times. And 2 times 60 is 120 degrees. Okay? So it's not terrible doing the conversion from one to the other. Now, the reason radians are going to be helpful for us is degrees are actually a man-made unit of measure. All right, degrees weren't discovered. Mankind decided that 360 degrees in one full revolution was a good idea. Many people assume that it's related to the number of days it takes planet Earth to travel around the sun, right? So it's kind of an earthy measurement. Whereas radians are actually more innate to the mathematics. Math likes radians better than degrees. All right. As mankind, we're typically used to using degrees, just like how here in America we're used to using inches, feet, and yards rather than metric system. So just be aware that radians and degrees, they measure the same type of thing. They're just different units to do it. Let's see. I want to draw just kind of a circle and have us kind of think about some of the degree and radian equivalents for this. Let's see if I can open up my toolbar, actually. I'm just going to draw a nice circle this time for fun. Actually, we might even draw two just to have it fit a little bit better. So there's one, and there's two. Not bad, not bad. So here's two circles. And let's think about this. I'm going to try to divvy these up. Terrible. All right, so let's think about degrees first of all. So over here is 0 degrees, here's 90 degrees, here's 180 degrees, and here is 270 degrees. And then 0 also coincides with 360, obviously, if we've completed a full revolution. So 0 is going to be the same as 0 radians, all right? And 360 is going to be the same as how many radians? How many radians were in one full revolution? 6.28, or we'll call that 2 pi. So 0 degrees, 0 radians makes sense. Well, I guess not for every unit of measure. If you think about Celsius and Fahrenheit, 0 degrees and 0 degrees do not line up, but that's for their own crazy scale. But for radians, 0 and 0 line up, and 360 and 2 pi line up. So if 360 equals 2 pi, 180 is equal to how much in radians? 1 pi, right? Half of 360 is 180, half of 2 pi is 1 pi. Okay? So think about this. This is the key idea that I always visualize, is half of the circle is pi radians. All right? Half of a circle is pi radians. So if I want 90 degrees, this is half of a circle, all right? And that sounds weird. But what's half of 180 is 90, right? So half of pi is going to be, I'd call that pi over 2. And let's say I divided the 90, again, in half. What is that in degrees? Right, 45 degrees. And half of pi over 2 is pi over 4. All right? Dividing a fraction in half, you can just double the denominator. And the other way I like to think about this is 1/4 of this full pi, right? So if I want this measurement, let's see, switch back to yellow. What is this measurement in degrees over here? 135 degrees, right? That is 3 45-degree angles added up. And this is 3 out of 4 slices for a full pi radians. So in radians, I would call this 3 pi over 4. Right? It's just 3 of these. Right? So 1, 2, 3. 3 pi over 4. Okay? So let's see if I can go past this. Well, 3 pi over 4 landing on pi, that's the same as 4 pi over 4, right? So another pi over 4 more than that is going to land on 5 pi over 4. And 5 pi over 4 is the same as how many in degrees? 225 degrees is right here. All right, sorry, yeah. Right, so 180 plus 45 landed me there. And this is 270 degrees. So this is 5 pi over 4, and I'm adding another pi over 4, so that's the same as, bless you, so that's 6 pi over 4, or what happens if I reduce that fraction? 3 pi over 2 radians. Right, and you could think of this whole region being 3.5 of the pi, right? Does that make sense? So, and 2 pi, notice, is going to be the same as 4 pi over 2, right? If I think about this as being full pi, a pi and a half, a full 2 pi's, right? But let's figure out this 45 reference angle in here first. 270 plus 45 is 315 degrees. And let's see, this one's maybe the trickiest one yet. Let's see. I'm adding a pi over 4. So yeah, 5 pi over 4. This is the same as 6 pi over 4, so that's 7 pi over 4 is what makes sense in terms of radians. So this way at least you kind of have like a visual representation, so you can kind of, actually my 7 looks a bit like a 2. So you can kind of think about where these land a little bit. Oh, that's a 7 pi over 4. Here we are. Bam. All right. So let's talk about what if I divided my pi a little bit differently. Let's see. What if I divided this into thirds? Let's see. So here's 180 degrees. Right. Here's we actually don't need the 90 this time. So here's 60 degrees. 120. All right, 180. Add another 60 to that, and we'd get 240. Oh, I'll keep writing them on the inside of the circle if I can remember to. Add another 60 to that, and we would have 300. And then add 60 to that, and we'd land at 360. Right? So what did this do to my pi units up here? This divided it into 3 slices. Let's see. So if this is pi, if I divide pi into 3 slices, 60 degrees is going to be the same as pi over 3 radians. 120 degrees is going to be the same as 2 pi over 3 radians, right? 2 of those 1/3 slices. Right? Pi landed on 3 pi over 3 slices, which makes sense. 3 over 3 reduces to 1 full pi. So 240 degrees is going to be 4 of those slices. So 4 pi over 3. And 300 degrees is going to be 5 of those slices. 5 pi over 3. And then 6 pi over 3 is 2 pi, right? 6 over 3 pi, or 6 pi over 3 reduces to 2 pi. And let's see, let's divide this up one more time. If I take 60 degrees and cut it in half, what do I get? 30 degrees, right? So there's 30, 60, 90, right? 120, 150, 180, and then plus 30, divide that in half. That's going to be 210. 240, 270, 300, and 330, right? And then 360. Now we've already hit the 90 and the 180 and the 270 with these ones over here, so I won't repeat those. But let's see, if pi over 3 is 60 degrees, what do you think 30 degrees is going to be? It's going to be half of that. Pi over 6, right? Yep. So let's see. So here's pi over 6. Let's see. Do you guys know a way we could write this? This one's a little trickier here. I could think of this. I could have thought of this as 4 pi over 6. So this must be 5 pi over 6. All right, let's see, 210. This would have been 6 pi over 6 here. So this is 7 pi over 6. And then let's see, we've already got that. To find 330, I'm adding a pi over 6 to this. So this would have been the same as 10 pi over 6, so that's 11 pi over 6. All right, so those are just some relationships between the radians and the degrees. I just wanted you to see where it landed on the unit circle, so you'd kind of be aware of that. And then you can kind of use this diagram a little bit to help you, figure out some things, and I think that can be helpful. So let's see. Let me ask you to do a question with this. Now this is going to be a bit of a stretch here, but let's evaluate what is cosine of 4 pi over 3. Cosine of 4 pi over 3. Well, we could go through the work of converting that to degrees and go from there, but let's actually try to do this radians the whole way, if this even makes any sense to us. So let's see, 4 pi over 3. First question I think of is this bigger or smaller than a pi? Bigger, because 3 pi over 3 is 1 pi. 4 pi over 3 is more than that, right? So whereabouts is that? Well, a pi would have landed right here. That would have been 3 pi over 3. So 4 pi over 3 is right around here, right? And now my question for us is, what would the reference angle be in radians? Pi over 3, right? Because 4 pi over 3 minus 3 pi over 3 would give me the 1 pi over 3 reference angle. All right? So cosine of 4 pi over 3, that's the same as, let's see, question, is cosine, what quadrants is cosine positive in? See, it's positive, negative, negative, positive, because cosine is the same as the x-coordinate. The x-coordinates to the right are positive, the x-coordinates to the left are negative. So I'm expecting this is going to be the same as the negative cosine of pi over 3. And let's see if I can figure out my pi over 3's here. It turns out the hand trick still works, but I might have to figure it out here. Let's see. Here's my hand. All right. So here's 0 pi. All right. This finger, my 30-degree finger, is the same as pi over 6. All right. This one would be pi over 4, or 45 degrees. This one is pi over 3, all right, or 60 degrees. And this one would be pi over 2, half of a pi, or 90 degrees. Okay? So my pi over 3 finger, if I put that down and I want to find cosine, cosine is the square root of the number of fingers to the right divided by 2. So the square root of 1 over 2, or 1/2. Yeah. All right, so I just want to point out that the hand trick still works. You just have to kind of change the way you think about things. So we are able to evaluate stuff like this, though, and it's not impossible. Not impossible. So, all right. So that's a whole bunch of stuff with that, but now we're going to actually talk about something that I think you've seen before in Math 2 or a geometry equivalent class. Question?
Can you put that in a calculator and have it come out right, or will the pi stuff come out?
Well, that's actually a really good question. Let's do that, since we've been working with pies and whatnot. So here's my calculator. Let me hit mode. Now the first thing I'm going to have to do is actually make sure I'm in radian mode and not degree mode. Okay, so the moment I'm entering in radians, it has to be able to communicate in that mode. So I wanted to calculate what the negative cosine of pi divided by 3 was, and I'd have to close parentheses on that. And if I hit enter, I do end up getting negative 0.5. So it's a really good question. I like that, because I forgot that I haven't showed you how to do radians yet. So yeah, so that's all you had to do was make sure you put it in radian mode as all you have to do. I like it. Let's see. Go on back to this. So so these next two skills, they're a little bit quicker. you've seen something like this before in a geometry class or a Math 2 equivalent, talking about arc length. All right? All right, so we're going to discover a formula for arc length. And I'm going to start with the following. Imagine two concentric circles with a central angle and an arc as a result. The inner circle is going to have the following dimensions. Its radius is 1, and that arc length there, all right, is going to be theta radians, or we can think about it like that, right? Theta is the angle that's forming it on the unit circle. And for the big circle, its radius we'll call r, and its arc length we'll call s. And actually, I'm not sure why they chose to use s for arc length. I don't remember why. Because, I mean, s is used for side length of a square, but I suppose they're starting to run out of letters here. We're already using Greek ones. So what I want to do is actually set up a ratio here based off of this sketch. All right. So this, the s to the theta, s over theta, is proportionally equivalent to r over what? Over 1. All right? The big arc to the little arc is equal to the big radius to the little radius. All right? So I've set up a proportion. And if I want to solve this equation for s, my arc length, what would I do to both sides? How do I get s by itself? Yeah, multiply both sides by theta. Right? So those would end up canceling out, and I'd end up getting s is equal to r theta. Okay, r times theta. And this is the formula for arc length. And what I want to point out is that r is in radians. Okay, so this formula does not work if you're, nope, I lied. R is in units of length. Theta is in radians. That would make more sense. Theta is our angle. Okay, so I can now actually use this formula to calculate the distance along an arc. Right? I mean, using trigonometry, you would have been able to find the straight line distance there, but it's not a straight line when it's along a curve like that, so it would be longer than the distance just between those 2 points in a straight line. So let's put this to use real quick, and then we'll derive one more formula. So let's do an example. Find the length of AB, and if I label AB with this little arc over it, it's referring to the length along the curve AB, not the straight line distance for the segment AB. All right. So let's see. Let's draw our circle. Let's say A is here, B is here. And let's label some facts. Suppose the radius here is 5. And let's suppose my angle measure, let's call this, well, it's bigger than pi over 2, which would have been like 90 degrees. Let's call this 3 pi over 4, perhaps. Not necessarily to scale. All right, so if I want to find the arc length from A to B, that's the distance I'm talking about, S, then all I have to do is kind of plug it in this formula. So S is going to equal the radius, which is 5, multiplied by my theta measured in radians. All right, so if this said 135 degrees, 5 times 135 is not going to give me an answer in units. Okay, so 5 times 3 pi over 4 is what I would end up getting. So I'd get S is equal to, that's the same as 15 pi over 4. Or that doesn't make as much sense to us as perhaps a decimal would in this case. So 15 times pi divided by 4, I get 11.78 units when I round. So it's kind of neat having such a simple formula to calculate the length of an arc. Technically, like I said, if I gave you degrees here, you could convert those degrees to radians and then plug it in, and it would work out for you, and it wouldn't be that impossible. And then the last thing, I know this lesson's getting long, but we're going to make it. The last thing that we're going to discover is about area of a sector. All right. And you've definitely seen this before, but we're going to think about it in terms of radians today, making a nice little formula for us. So suppose I've got a dimension here. I'll call this R and S. All right, so there's kind of the arc length there. The radius is R. It's got some sort of theta. So if I want to set up a ratio here, or proportion rather, to calculate the area of this section, all right? Now the area of that section, all right, I guess I could call it A. So theta is the angle, A is the area. We could write a little proportion. A over, comparing the area of this slice to the area of the whole circle. What's the equation for the area of this whole circle?
2 pi?
No, not quite. Pi r squared. That formula will come up in a second though. So the ratio of the area of our sector over the area of the whole circle. All right, so far you see the ratio we're talking about. That should equal the length of the arc, all right, compared to the circumference of the whole circle, right? Those ratios should be the same. So the ratio, or the length of our arc is what in units, or in terms of this? We just had the formula a moment ago.
R theta.
R theta, right? And the circumference of a circle? No. Circumference? That's the 2 pi r. Yep. All right, so one thing I'll just label for this right here is this is the length of arc. All right. This is the circumference, and this is the area of whole circle. Right? So so those ratios I think make sense. That proportion perhaps makes sense to you. And if I wanted to solve this equation for A, the area of just the sector here, just the piece that I'm looking for, what could I do to both sides? I want to get rid of this. Yeah, multiply both sides entirely by pi r squared. And I'm going to end up getting the following. A equals, right, so this cancels out fully. Let's see what we got here. So this r and this r cancel out. This pi and this pi cancel out. 2 in the denominator, I'm going to write that as 1/2. I'll have an r squared theta. And this is the area of a sector. All right, and this only works if theta is in radians. Okay, and I believe we have to get going in just a moment. So I won't have time for an example, but have a great day.